Section 2.4 in college algebra is specific to the complex number I, and you did learn about this back in Algebra 2, but we have the real number system and we also have the imaginary number system. And when we had to work with imaginary numbers, we had to learn a little bit about the number I. So, explain each of the following true statements. A complex number may also be a real number. Well, a complex number is in the form a plus bi. And the imaginary component is the b, so if b happens to be equal to 0, meaning there's no imaginary component, a real number is going to be the answer. So for instance, 3 plus 0i is really just the number 3. And then a complex number might not be imaginary. I think that's the same question. So we're going to move on. Number 3 says identify each number as a real or imaginary number. So negative 5 is a real number. Pi is also a real number. It's irrational, but it's real. And then I squared to 6 is an imaginary number. Negative 3i is an imaginary number. 2 plus 5i is an imaginary number or complex number. And then negative 7 minus 6i has an imaginary component right there, so complex number with an imaginary part. 9 through 16, they want us to write each number without a negative radicand. So we're going to have to incorporate the idea that we learned back in Algebra 2 that said I was the same thing as the square root of negative 1. So when I think about square root of 100, I could break them up into the square root of 100 times the square root of negative 1. Well, I know square root of 100 is 10, and then square root of negative 1 is I. So negative 100 square rooted is just 10i. Some people think of it as poking the eyes out of it. Now be careful on 10, there's a negative coefficient that was just going to come along for the ride. When I break down the square root of 400 and negative 1, I think of that as 20i, but since there's a negative coefficient, it's negative 20i is my final answer. And then 39 doesn't simplify the number at all, but I can think about taking the negative 1 radical out of that. So the negative coefficient, and then we're going to have an I in front, and then the square root of 39 is left over. And then the square root of negative 4i, that is really the same thing as a 2i, so my final answer is 5 plus 2i. Negative 50, we're going to break into 25 times negative 1 times 2. Well, so we have 9 minus 25 is 5. Negative 1 square rooted is I. And the square root of 2 is going to remain a radical. Be careful on 14. A lot of children think they just push negative 5 times negative 5 together, and then that creates a positive 25. But when you do that, you lose the imaginary component. So what you actually have to do is pull the I out of both of them first. And then when you multiply these numbers together, you get I squared, and then square root of 5 times square root of 5 is 5. But then remember, if this I equals the square root of negative 1, if I square both sides, I squared equals negative 1. So this is really a negative 1 times 5, or a negative 5. And had you not pulled those i's out at the beginning of the problem, you wouldn't see that. We're going to have a similar issue here on number 15. You need to pull the i's out of the problem first. This time, however, we're going to see something kind of amazing happen. Square root of 40 over 10 is really just the square root of 4. And the i's here indeed will cancel. So the answer to this question is just 2. And I think you guys all know by this point that your calculator does have a complex mode, imaginary mode. Please try to avoid it because I want you to be able to do this without using your calculator's complex mode. And if I think people are cheating and using the calculator, I'm going to have to give you a calculator-free quiz. Okay, 16. You can pull the I out first, but I do notice that 54 and 9 can reduce to 6. So this is really like the square root of negative 6. So when I take the I out, eventually it's I squared to 6. Then we're going to add and subtract complex numbers and write the answer in standard form. That just means they want the answer written in A plus BI form. So 3 plus 4 is 7, 2i plus negative 3i is negative 1i, 4 plus 2 is 6, negative 1i plus 5i is positive 4i, Negative 2 minus negative 4 is negative 2 plus 4, so that's 2. And then 3i minus 3i is no imaginary part, so the final answer is just 2. Negative 3 minus negative 4 is negative 3 plus 4, so that's a 1. 5i minus 3i is plus 2i. This is getting a little boring. 2 minus 3 plus 2 is, let's see, negative 1, 2, 1. Negative 5 minus 4, negative 9 minus another 1 is negative 10i. And then negative 4 minus 2 is negative 6, minus another 4 is negative 10. Negative 1 minus 3 is negative 4. Negative 4 plus 5 is positive 1i. Now when we multiply complex numbers together, it looks really similar to a FOIL problem, but we're going to have an extra step of work at the end. So 4 times negative 1 is negative 4, and then outer is positive 12i, inner is negative 4i, and then last is going to be a positive 12i squared. Now there's two things we got to worry about. Obviously we've got some like terms in the middle. The other issue is we know I squared is really the number negative 1. So this is a 12 times a negative 1 on the back side, which makes this just the number negative 12. So now I've got some other like terms to collect. I've got the negative 4 and then later on the minus 12. So my final answer in standard form is negative 16, and then that'll become a plus 8i. Negative 3 plus 2i quantity squared, remember this is a FOIL problem, so if you need to write them out twice like this, please do so. Negative 3 times negative 3 is 9, and then we have minus 6i minus another 6i, and then plus 4i squared. Well, I know that I squared is really just a negative 1, so this is really a minus 4. 9 minus 4 is a 5, and then negative 6 minus 6 is minus 12i. 25, 2 times 2 is 4. We have a negative 6i on the outside, a positive 6 on the inside. Those are going to cancel because what we just found was two, what they call complex conjugates being multiplied together. The 6i and negative 6i will cancel. This becomes a positive 9 when you multiply it by the negative 1. So my final answer to that question is 13. On 26, I'm going to FOIL together the binomials, and then I'll multiply everything by an I when I'm done. So, let's see, 6 plus 12i minus 8i, oops, and then minus 16i squared. So when I try to simplify what's on the inside here, this is 6, it'll be plus 16, so that'll be a 22, and then plus 4i, and then when I distribute the I to everybody, I'm going to get 22i plus 4i squared, but remember I squared is a negative 1, so I think what I really have is negative 4 plus 22i when I write it in standard form. 27 is the same idea, we just got weird radicals. So square root of 6 times square root of 6 is 6. Again, we have conjugates, so negative I squared to 6 and then positive I squared to 6 will cancel each other out. And then we've got a negative I squared. So those cancel. 6 minus a negative 1 is really 6 plus 1, so I think we get the answer of 7. Alright, finding powers. These are kind of fun. So, I to the first power is just I. We know I to the second power is a negative 1. So I to the third power would be the same thing, well, it's kind of the same thing as well, it is the same thing as I squared times I to the first. So that would be like I times negative 1, so it's a negative, negative I. And then I to the fourth power would be negative 1 squared, so that would be a positive 1. And then you'll notice if you continue on in the list, the cycle just keeps repeating over and over again. So I, negative 1, negative I, 1. I, negative 1, negative I, 1. So when I look at I to the fifth power, again you could continue the list, or you could think of it as being I to the fourth power, times an I to the first power, because that would be the same thing as I to the fifth power when you use your exponent properties. Well, I know I to the fourth power is a 1, and I to the first power is an I, and 1 times I is just simply I. I to the eighth, you could break it up a few different ways. I like to think of it as I to the fourth power that has been squared, because that would be the same as I to the eighth. Well, I know I to the fourth power is a 1, and then when I square a 1, I get a 1. I to the ninth is, well, again, a couple different ways we can think about it. It's like saying, oh geez, so many ways. Let's do I to the 8th, which we just found, times another I to the 1st. So I to the 8th is a 1, we just realized, and then I to the 1st is I, so he's I. And again, you can continue on through the list and loop through, or you could say I to the 11th would be the same thing as, let's see, well, I to the, gosh, so many options. Well, we just did I to the 9th, we'll put that in, and then I squared. So I to the 9th we just found to be I squared we know is a -1, I times -1 is negative I. Oh goodness, 43. So I to the 43 is kind of like I to the 42 with another I, so let's think of it that way for a second. Now, I know what I is, but let's talk about I to the 42. I to the 42 is like I squared to the 21st power. So I squared, really just a -1. Well, if I take a -1 and raise it to an odd power, it's just going to end up giving me the answer of -1, because -1 to an odd power is -1. If I multiply him by that extra I, my answer is -I. And then I to the -6 is really the same thing as 1 over I to the 6, because negative exponents throw it to the denominator. Couple different ways you can think about this. I to the 6th power is really I to the 3rd power that's been squared. And I see from my list up here, I to the 3rd power is just -I. So what I have is -I squared in my denominator. So I have 1 over I squared, which is 1 over -1, which is -1. Oof, that was exhausting. Okay. I to the 1 over I to the 9th. I think I already found I to the 9th. It was I. So I think we could just write it as 1 over I. And I'm okay with that. Technically that's not rationalized, and you'll encounter some math teachers who won't accept that answer, but I will. And then I to the 12th power. Let's see. I think, well, alright. Whoops, that's a 1. I to the 12th is like saying I squared to the 6th power. Well, I squared is just a -1. So if I take a -1 and raise it to an even exponent, that's going to create a positive 1, and 1 over 1 is 1. Okay, dividing complex numbers. We're not allowed to leave them in this form because we know that I is really the square root of a -1, so it's improper to leave a radical in the denominator. So your Algebra 2 teacher would have you multiply both numerator and denominator by what's called the conjugate of the denominator. So the conjugate of the denominator is his evil twin, I call it. So instead of 1 minus I, he's 1 plus I. So the B term is going to have the opposite sign. And then to keep the fraction balanced, as long as you multiply both numerator and denominator by that, you're going to be fine. So on 36, 1 times 1 is 1, and then 1I plus another I is plus 2I. I times I is I squared. Now we'll clean that up in a minute. And my denominator, some great things happen. The outer inner part of the FOIL problem will cancel, that's what conjugates do, and then -I times I is a -I squared. So what we end up with in the numerator is 1, and then later on a -1, so nothing, and then 2I, and then here 1 minus -1 is really just a 2. So my final answer for this particular question, it's kind of boring, it's just I. The conjugate for number 37 is going to be the evil twin of the denominator, so 2 minus I. So up in my numerator we've got 4, and then -2I minus another 2I is -4I plus I squared. My denominator is going to be a conjugate set, so we're going to have 4, outer inner will cancel, and then minus I squared. And then I'm going to see 4 and later on a -1, which is a 3 minus 4I, all over 4 minus -1, which is a 5. Now, standard form needs to be an A plus BI form, so you're going to have to take that 5 and distribute him under both terms in the numerator, And that is the answer they're going to be looking for. Again, I know your calculator can do this work, but if I catch you trying to use your calculator and not showing all the work you need, you're going to have to do a calculator-free exam, so please don't do that. The conjugate of the denominator for number 38 is 1 minus I. So multiplying through the numerator, we get 1, and then negative 3i plus a negative 1i is negative 4i. Negative 3i times negative 1i is a positive 3i squared. My denominator's conjugates become 1 and then a minus I squared. And when I simplify all that, let's see, I got 1, and this will be a minus 3, so negative 2 minus 4i. 1 minus negative 1 is a 2. So distributing this 2 underneath both parts and writing it in standard form, it's going to become a negative 1 minus 2i. So sometimes they show up kind of pretty for answers and sometimes not. And then the conjugate here on number 39 is 2 plus I. So multiplying the numerators together, we get negative 6. 8 minus 3 is plus 5i. Plus, 4i squared. The conjugates on the denominator are 4 minus I squared. Negative 6 minus 4, let's see, is negative 10. Plus 5i over 4 minus negative 1 is a 5. When I distribute this 5 under both parts, I get negative 2. Whoops, that's a 2, plus or minus I. And I guess that's it.